Well, welcome back, everyone. This is section 3. Mrs. Hansen here, ready to talk about solubility, some general features, and then the next section, more specific features. So let's begin by defining the term solubility. Where are we in terms of your notes? Like the bottom of page 3 or so for section 3 on solubility. To define the term, we're going to say it's the amount of solute that dissolves in a given amount of solvent. So we want to define the term solubility. How much solute dissolves in a given amount of solvent? Remember, the solute is what we have the least of, and the solvent is what you have the most of in a homogeneous solution. We typically report solubility in terms of grams of solute per 100 mils of solution. Grams of solute per 100 mils of solution. If a solution is saturated, it is holding as much solute as it possibly can. It's holding the maximum number of grams of solute that can dissolve. There is no more room for additional solute. It's filled up. And then if we have an unsaturated solution, it's containing less than the maximum number. There is room to dissolve more. So when I think about saturation, if a solution is holding as much as it possibly can, we call it saturated. If it has room to take in more, we call it unsaturated. And the terms that we use to define that is grams of solute per 100 mils of solution. The general term of solubility, will a solution form, can be summed up with a general saying of likes dissolve likes. Will a solution form? Will the solute actually dissolve in the solvent? And the answer is yes, if polar dissolved in polar or ionic dissolves in polar, because they are both charged substances. Here we have kind of a close view of sodium chloride. Sodium chloride as a solid dissociates when it's put into water and forms aqueous ions of sodium and an aqueous ion of chloride. Based on the polarity of the water, remember that water is a very polar substance. We have a negative region on top of the oxygen. It's a very electron-rich area. And we have a positive region on those hydrogens. It's a very electron-deficient area. Knowing that sodium and chloride are also charged, you'll see that the positive ion of sodium is highly attracted to the negative oxygens. And you'll see that the water actually surrounds the sodium. Draw this with me, where the oxygen with its electron-rich area surrounds the sodium ion and helps to stabilize that charge. And remember how chloride was negative? And so you got it. Remember how the hydrogens then would surround the chloride based on opposite charges. So you'll see that the negatives ions are stabilized by the positive area on the polar water molecule. And here's an example of the dissociated form where you can see the chloride ion, Cl negative, being surrounded by those hydrogens based on opposite charges. This would represent the sodium ion being surrounded by the negative oxygens. Opposites attract, and therefore the polarity of the water molecule helped to break apart sodium chloride and surround the solution. So you can see that the water has a stronger attraction for the ions than the ions had for one another because they are separated once placed into water. Small neutral molecules with oxygen or nitrogen can actually form hydrogen bonds to the water and are water soluble. So here you can see, even though ethanol, if I were to write out ethanol's Lewis dot structure, we'd have CH3, CH2OH. This is a very polar region of the molecule, meaning that I have a very electron-rich oxygen, making that area partial negative. I also have a non-polar area in the hydrocarbon chain and a nice positive charge over here for this as well. So you can see a hydrogen bond forming between the water and the alcohol unit, the OH unit, on ethanol. That helps to create solubility. So likes dissolve likes. Polar will dissolve with polar. Whoops. Ionic compounds, which are also charged, will dissolve in a polar solvent as well. But will not happen is one of each. A nonpolar with polar simply doesn't form a solution. Nonpolar compounds are soluble in nonpolar solvents. Likes dissolve likes. Octane, which is a long, boring molecule, 8 carbons in a row, 1, 2, 3, 4, 5, 6, 7, 8. All of these hydrogens fill up the requirement of 4 bonds for the carbon chain. So C8H18, a long carbon chain. This is a non-polar molecule. Here you have carbon tetrachloride. Carbon in the center, 4 chlorine around. Carbon tetrachloride is also nonpolar. And when I place nonpolar in nonpolar, we get a homogeneous solution forming where the molecules are not attracted, they are not repelled, therefore they just blend uniformly together. A uniform blend creating a homogeneous mixture. Remember, they're exhibiting London dispersion forces since they are nonpolar molecules. Here's stearic acid and water. Now let's take a look at this molecule. Stearic acid has an incredibly long nonpolar carbon chain. And it has a little bit of an exciting area over here that is a polar region, the COOH carboxylic acid group. Here we have a small polar region and an incredibly large non-polar region. So what wins? Well, stearic acid and water insoluble because this is just too small to overcome the large nonpolar area. So here's a nice little water molecule that would like to interact with this part of the stearic acid molecule, but this long chain of nonpolar region dominates this intermolecular attraction. Therefore, it is not soluble in water. Even though I have a nice little polar area, this is way too big, and that nonpolar area makes it insoluble in water. The process called solvation. It's known as the process of dissolving a solute into the solvent, and it's a physical process, and it's accompanied by an energy change, as all physical changes are, as well as chemical changes. I mean, it takes energy to separate the particles of a solute. Sodium chloride, as a solid, has electrostatic attraction between the positive and negative ions. In order to separate them, the water molecule has to be able to go in and surround the sodium and break it free. The other part of the water molecule surrounds the chloride and breaks it free. You must separate the two ions, and that requires energy. So when you think about energy, think about that in terms of joules or calories. If it's a requirement, we put it on the left side of the arrow. Energy must be supplied to force the ions to separate. Now, when it separates and the water surrounds it, those are forming new attractions, and that part actually releases the energy. So when sodium ion is being surrounded by the water molecule based on opposite charges, this is a release of energy, this process known as solvolysis. And of course, the chloride with its negative, it's going to be surrounded by the positive hydrogens on the water molecule, and that's a stabilizing force. Therefore, it releases energy. That process that releases more energy than required gives us an exothermic reaction overall. And if the separation requires more energy than it does in terms of releasing as it's solvated, we call it an endothermic process. So dissolving is typically exothermic. It is a heat releasing process, but there are exceptions to that rule, as chemical cold packs, for example, would illustrate. Let's predict the water solubility of each substance. Does a solution form? So just the question is, will they dissolve in water? Well, letter A is potassium chloride. Did you recognize this as an ionic salt? It's built of a metal and a nonmetal. When KCl is dissolved into water, it is a strong electrolyte. It 100% dissociates and releases aqueous ions. So yes, because it's a salt, it is water soluble. Ionic salts that are water soluble dissociate.
Hansen here from Western Michigan University.
Let me pause this. So sorry for that interruption. I had a video start playing. I had to pause this and grab that one. So we were talking about solubility. We said potassium chloride is an ionic salt. So yes, it is water soluble. Letter B is methanol. And the answer here is, although this is not an ionic compound, it is a polar substance. The polarity of this molecule in this highly charged area, you have a very electron-rich oxygen, making it partial negative, and a partial positive, again, just based on the polarity of the bond and on the structure of the molecule. Likes dissolve likes. And so, yes, this will also be water soluble. Here we had a polar solute, which is the methanol, in a polar solvent, which is the water. And so, yes, likes dissolve likes. And letter C, we have hexane. This is a 6-carbon chain. 1, 2, 3, 4, 5, 6. The hydrogens are placed then to just fill the 4-bond requirement of each of those carbons. Each one of these leads to a hydrogen, of course. This is a non-polar solute. Nothing interesting on that molecule at all. It is all non-polar. And of course, water with its polarity, this would be a no. This will not form a solution. In order to form, we need an ionic salt, or we need a polar molecule. But a non-polar solute with a polar solvent will not form a solution. How about you try some? Answer the compounds and determine if they are going to be water soluble. Come back to me when ready. All right, so how did you do? Letter A is sodium nitrite. This is a water soluble salt. This is made of a sodium ion and a nitrate polyatomic ion. When placed into water, it is a strong electrolyte and will dissociate into aqueous ions. So yes, this is water soluble. All soluble salts are strong electrolytes. How about letter B? This is a very boring molecule, isn't it? This is methane, CH4. When I visualize methane as a carbon in the center, 4 hydrogens around, you can see that this is non-polar, and therefore, no, it will not dissolve in water. Likes must dissolve likes. Letter C, already drawn for us, and gives us a couple of exciting areas over here, doesn't it? A couple of OH groups there, meaning that this is a very polar portion of the molecule. This is also a very polar portion of the molecule. Yes, this will form a solution with water, who is also polar. Remember, water, all kinds of HO bonds. KBr, potassium bromide, an aqueous salt. So when it is placed into water, an aqueous ion of potassium and an aqueous ion of bromide form. Those are charged ions. So yes, a solution will form. NH2OH, think about what this looks like. You have a hydrogen leading to a nitrogen, then an O, then an H. We can see all kinds of polar regions. We have a very electron-rich area on the nitrogen, as well as electron-rich area oxygen, and these partial positives just based on polarity of the bonds. And so this is a polar solute, and so yes, this will also form a solution with water. Likes dissolve likes. Look for ionic salts or look for polar molecules. The only one that did not form a solution was the nonpolar methane. Which pairs of compounds form a solution? Likes dissolve likes. Give yourself time to think, pausing the video. Come back when you're ready to check. Do some think time first. Welcome back. How about letter A? Benzene and hexane. Benzene is a hydrocarbon. It is a non-polar, very boring molecule. Hexane, also non-polar, just all carbon-hydrogen bonds. Non-polar with non-polar. Yes, this will form a solution. Letter B, sodium sulfate. Sodium sulfate in water. And I want you to recognize that this sodium sulfate is an ionic compound. It's built of ions. When this dissociates, two aqueous ions of sodium and one aqueous ion of sulfate dissociate. Remember, sulfate with its -2 charge, it requires 2 units of sodium to balance the charge. So we have 2 aqueous ions of sodium that dissociate, Na+, Na+, and a sulfate aqueous ion. So there's a total of 3 ions released. But yes, it will form a solution. It is a water-soluble salt. How about letter C? Here we have sodium chloride in hexane. Well, think about this. Sodium chloride is an ionic compound built of charges. Hexane is a non-polar, boring molecule. Non-polar and an ionic salt, those are not alike, so no solution will form. Water, we know to be polar. Carbon tetrachloride was non-polar, so no, likes must dissolve with likes. You need polar with polar or non-polar with non-polar in order to have a solution form. Let's talk about some additional concepts of solubility next. It says, although ionic compounds are generally soluble, some are not. The crystalline solid must have a stronger intermolecular attraction for each other than it does to the water, and therefore water cannot separate those into aqueous ions. So here we have a kind of a general rule to predict if salts will be soluble. Let's go through these kind of slowly together. And this is just from our textbook, and I just copied and pasted from our textbook. How do I know if a salt is going to be water soluble? Well, the first general guideline or rule says a compound is always soluble if it contains one of the following positive cations: lithium, sodium, potassium, rubidium, cesium. These are all group 1A metals. So if your first name of a salt starts with a first family metal, it's always soluble. And the same is true for the polyatomic ion, ammonium. It is always soluble. So if you see a first name in a salt from a first family metal or with the polyatomic ion ammonium, you know that salt will be water soluble. Now, let's talk about the negative ions. It says if, rule 2, a compound is soluble if it contains one of the following anions. The halogens, chloride, bromide, iodide, except for silver, mercury, or lead. These are the heavy metals. Silver chloride, non-soluble. Silver bromide, not soluble. See how I'm doing that? Silver is a solubility rule breaker. Lead iodide, not soluble. Mercury 2 iodide, not soluble. So here we're getting an idea that mercury, silver, and lead, those heavy metals, force the precipitation out, force it to be insoluble. Halides are generally soluble, except if the first name is silver, mercury, or lead. And if you see the last name nitrate, always soluble. You see the last name acetate, which is also written as C2H3O2 negative. It's always soluble. Sulfates are generally soluble except for barium, mercury, or lead. Now, I do not expect you to memorize these. As a matter of fact, I have a little different test-taking tool page that I like to use in addition to the solubility rules I just listed. I find this chart to be a little friendlier to use, and you are provided this also in your test-taking tool pages. You probably just never noticed it because you have to scroll pretty far down in your quiz, the last question of your quiz where your tool pages are provided. It's in there. You just probably never looked hard because you didn't need it yet. Let's learn how to use this chart as well. Will a salt be soluble? So is a salt soluble? In green, you'll see that the word SOL for solubility. The yellow is slightly soluble and the reds are insoluble. They do not dissolve in water. Now, a moment ago I said things such as ammonium, lithium, sodium, potassium, rubidium. Remember how they were always soluble? Look at this. Top is ammonium, lithium, sodium, potassium. The first family metals along with the ammonium. Only one exception, and that's lithium phosphate. See how I'm reading this? I find the first name up top, I find the last name on the side, and I hook them together, and I can see if it's soluble or insoluble. Let's say, for example, potassium hydroxide, KOH. Is that water soluble or not? First name potassium, so I find this column. Last name hydroxide, so I find this row. I hook together KOH, and in the box it tells me that it is water soluble. How about silver chloride? Is that soluble or insoluble? Well, here's the first name silver. Here's the last name chloride. So I hook together those two and I find this box. Silver chloride is not soluble in water, as we said on the previous slide. So I like this chart because it helps me just find first names on the top, and on the side are the negative ions, and I just hook them together and read where they intersect if it will be water soluble or insoluble. Let's practice that. Use the solubility rules to predict whether the following ionic compounds are soluble in water. You have sodium phosphate, magnesium phosphate, and potassium hydroxide. Take a moment with your solubility table and tell me what you see. Pausing the video. Okay, well, welcome back. Let me clear this off and we'll start fresh. The first one we had said to practice with was sodium phosphate, Na3PO4. First name sodium, last name phosphate. When I hook those together, sodium phosphate, this is the box I land in, and clearly I can see that yes, this is water soluble. What comes out? When I place this salt into solution, I would get 3 aqueous ions of sodium and 1 aqueous ion of phosphate. Phosphate carrying a -3 charge. It has 3 equivalents per mole. Sodium carries a +1 charge. So remember, you have phosphate with a magnitude of a -3. It takes 3 positive sodium ions to balance the charge. So a total of 4 ions would come out when that separates from its salt into aqueous ions. A total of 4 ions are now dissolved in that water. The next one you asked was magnesium phosphate. Magnesium phosphate, Mg3PO4, taken twice. All right, so how did you find that one? Here's the magnesium. Here's our phosphate. When I find them and intersect those row and column, I land right here at this box. That means that this is insoluble. It does not dissolve in water. So there's no aqueous ions. So this would be a non-electrolyte. No ions form because it does not separate, which just means that the attractions between the magnesium and the phosphate are much stronger than they are between magnesium and water. You had one more. You had potassium hydroxide. Potassium hydroxide. So you found the first name potassium. Here's potassium. Here's hydroxide. You find that that is soluble. So that is an electrolyte. Out comes a potassium ion and an aqueous ion of, and yes, this is soluble. 2 ions are released from solution, a potassium with a +1 and a hydroxide with a -1. Take a little bit of time and go through these examples, just indicating if they are soluble or insoluble. Come back to me when ready. I hear the dogs barking. I'm going to pause for a moment. Okay, well, I'm back. I had someone knock at the doors. So how did you do? Were you able to follow the solubility rules to tell me if they were soluble or insoluble ionic compounds? The first given was lithium carbonate. And I'm practicing your nomenclature so that that becomes familiar with you. Carbonate. So I found lithium, first name, carbonate, the last name, and when I hook those together, I find this box, and it is soluble. That tells me that lithium carbonate is an electrolyte, a strong electrolyte, Li2CO3. When it dissolves into water, 2 aqueous ions of lithium are released, and 1 aqueous ion of carbonate are released. Carbonate is a -2 ion, 2 equivalents, telling me I need 2 +1 lithiums to balance the charge. So there are a total of 3 ions that are released when lithium carbonate dissolves. It is a strong electrolyte. How about letter B? Magnesium carbonate. You found magnesium, Mg, carbonate, same row here, and the box tells me it's insoluble, meaning for letter B, MgCO3 is insoluble. It does not dissolve in water, telling me it's a non-electrolyte. It does not break apart into ions. Letter C, potassium bromide. Here's your potassium. Here's your bromide. So yes, you can see that it's soluble. That tells me that it is an electrolyte. A solution will form when placing it into water, releasing aqueous ions of potassium and an aqueous ion of bromide. 2 ions are released. Letter D, lead 2 sulfate. Remember that Roman numeral is required when naming a transition metal. Lead 2 sulfate. Here's your Pb plus 2, lead 2. Here's your sulfate. When I hook that together, I see that it is insoluble. So PbSO4 is insoluble, does not separate, it does not dissolve, meaning it is a non-electrolyte. Letter E, calcium chloride. Here's your calcium. Hooking to a chloride, we see that it is soluble. Calcium chloride is soluble. So yes, a solution will form and an aqueous ion of calcium with its plus 2 charge and 2 units of a chloride dissociate. There would be a total of 3 ions released when that solution forms. And there's a letter F, magnesium chloride, MgCl2. Where did you find that one? Magnesium chloride. Well, here's your magnesium. Here's your chloride. So you can see that that is soluble. So yes, a solution forms. And out comes an aqueous ion of magnesium carrying its plus 2 charge and 2 aqueous ions of chloride, each at a minus 1. There would be a total of 3 ions released when that solution forms. Remember the magnitude of the charge. Magnesium with its plus 2 would require 2 separate chlorides to balance the charge because it only carries a minus 1. That gives me a total of 3 ions that dissociate when magnesium chloride forms a solution. I like this solubility table. It's very easy to use and makes, looking at this chart friendlier than trying to memorize some solubility rules. Looking at the solubility rule for ionic compounds, let's try to use it to explain why milk of magnesia, MOM, right? From our commercials, milk of magnesia, it's an antacid. If you have an upset stomach, you might take some milk of magnesia to help neutralize the excess acid. Explain why milk of magnesia in water is called a heterogeneous mixture rather than a solution. Earlier we called this a suspension. If you've ever used milk of magnesia, it's white and you have to shake it a whole lot before you use it because it settles out. Look at where magnesium hydroxide, notice that it's an insoluble substance. MgOH taken twice is insoluble, meaning that it does not form a homogeneous mixture, which we call a solution. So therefore, it's classified as a suspension, which is a heterogeneous mixture. And I remember that those solute particles settle out over time. And before you use it, you better shake it well because all the active ingredient is sitting at the bottom, settled out, and you have to shake it and kind of get those the particles back into the suspension before delivering the medicine. How long have we been talking? Let's see. About 34 minutes. I think I'll take a little break, pause, and you might want to do the same. Come back when ready, and we'll pick up with solubility, effects of temperature and pressure. I'm just going to take a little break. Okay, I'm back. Let's take a quick peek at how temperature and pressure affect solubility. For most ionic and molecular solids, so molecular solids, they still have to be polar for this to form a solution. Ionic compounds we commonly call salts. Molecular compounds are polar compounds. As we warm up a solution, solubility generally increases. With increasing temperature, solubility will also increase generally for solid solutes. We're going to see a different trend if it's a gas dissolved in water. Let's say, for example, here's sodium nitrate, NaNO3. I see a direct correlation that I can look at this solubility graph and say that generally I can get more solid to dissolve as the temperature warms up. Notice we have temperature increasing on the x-axis. Solubility is being measured in grams of solute per 100 grams of water. A positive slope. More salt dissolves as the temperature increases. Potassium nitrate has a nice solubility curve where I can see a drastic increase in the amount of salt dissolving in the water as the temperature rises. Do you see this guy? He's a rule breaker, isn't he? That's cobalt 3 sulfate. It generally decreases for whatever reason. So the ionic bonds actually increase in strength as you warm up the temperature, but this is an outlier to the general trend. Generally, salts, as you warm them up, will increase their solubility. We can actually read these graphs and tell me the solubility at a specific temperature. So for instance, if I wanted to know the solubility, let's say of potassium nitrate at 50 degrees, or what might be easier to read. Here's a nice intersection right here. Here's the potassium nitrate. This is the line I'm referring to, KNO3. At 20 degrees Celsius, I have 30 grams of potassium nitrate in 100 grams of water. So I'm reading the solubility table. Here's another nice intersection, just roughly, I'll say right here. This is sodium nitrate. At 10 degrees Celsius, 80 grams of sodium nitrate dissolve in every 100 grams of water. So that's the solubility. How many grams per 100 grams can dissolve at a specific temperature? By dissolving a solid in a solvent at high temperature and then allowing it to cool very slowly, undisturbed, without knocking it, bumping it, letting dust settle on it or anything, a supersaturated solution can form. Supersaturated solution. Now that's defined as a solution that you make. It doesn't happen naturally. A supersaturated solution is one that contains more than the predicted amount. And here's how you do it. You take a solution that is saturated at a specific temperature and you warm it up. All of this extra salt that was sitting at the bottom is now dissolved. At the 70 degrees, I see no solid at the bottom. Then I let it cool again and look at no solid at the bottom. This now is saturated. When I start at 25 degrees and it's holding all it possibly can, so much so that there's extra on the bottom, I warm it up to get it all to disappear and I just let it cool. And look at, none fell out. All the extra is still in solution. These are pretty cool to watch. Here we have a supersaturated solution and I bump it, or I add a seed crystal. I do something to agitate it and all of the excess begins to fall out of solution. And all of the excess falls out, you're going to go back to a saturated solution. So here you had a supersaturated, then we agitated it, and all of the excess solute fell out. A supersaturated solution is one in which it's holding more solute than the graph would normally predict. Now, for gases, we actually see an opposite trend. The solubility of a gas decreases with rising temperature. So for gases, you increase temperature and the gas decreases solubility. This is actually a process known as thermal pollution. For example, when a power plant, something that is releasing warm water into a nearby lake, let's just say a power plant is famous for this, as they use the lake water to cool down their equipment and then just simply put water back into the lake, but it's warmer. When you release warm water back into the lake, the dissolved oxygen levels decrease. And what happens? Leads to a fish kill. You'll start to see fish die off, and you'll see them either just floating on the surface or wash up on the shore. That true tale sign of if whatever it might be, whatever plant or factory is on water, and you see a buildup of fish kill around it, you know that they're releasing hot water back into the lake. And when you raise the temperature of that water up, you decrease the levels of oxygen. It comes bubbling out of solution, and with decreased oxygen content, you're going to have a decreased marine life. Whoops. So when we think about temperature, we can think of the direct relationship for solids, an indirect relationship for gases. How about pressure? Let's talk about the effects of pressure on the solubility of gases. Henry's law will state that the solubility of a gas in a dissolved liquid is proportional to the partial pressure of the gas above the liquid. Henry's law tells us that if I increase the pressure pushing down on the surface of a liquid, the gas will stay dissolved. That simply means that, think of a can of pop. It's sealed to keep the carbonated beverage with the carbon dioxide bubbles in solution. And when you release the pressure, you see those bubbles come out of solution. So with a closed can of soda, you have high pressure above here. So just think about that. Here's the liquid in a sealed container. The increased pressure on the surface forces the gas to stay in solution. A closed container increases pressure on the surface of the liquid here, forcing the gas bubbles to stay here, right? So here's your little carbon dioxide bubbles in solution. When you release the can, so here all of a sudden now the can is open and the pressure then is released. All of this excess pressure then drops, and therefore you start to see the bubbles, and it will come out of solution. You open the can of soda, drops the pressure, carbon dioxide then comes bubbling out of solution. So Henry's law, increase the pressure above, pushing down on the surface, you're going to force more gas to stay in the solution. If you release the pressure by opening the can, the gas that was forced in solution comes bubbling out, and you've lowered the solubility. Solubility and pressure are directly related. If you have increased pressure, you'll have increased solubility. And remember, we're talking about gases. Gases and their behavior is affected by pressure. If I push down on the surface of this liquid, I can force more gas molecules into solution. If I release the pressure, the gas molecules come out of solution. Pressure and solubility are directly related. This is known as Henry's law. So let's predict the effect on each change on the solubility of sodium carbonate, which is a solid, And nitrogen, which is a molecular nitrogen, which is a gas. And you see how I'm pulling that out? Ionic compounds are solids at room temperature. Nitrogen is a gas. So let's take the increasing the temperature first of sodium carbonate. We said that increasing the temperature of solids increases the solubility of solids. Let me do this better. Letter A, we'll do sodium carbonate, and we'll talk about nitrogen and each of these. All right, so we'll do A, B, C, D. I think what I'd like to do is just make a grid like this. Keep in mind that this is a solid and this is a gas. So in letter A, if we raise the temperature, we're going to increase solubility. If we increase the temperature of a gas, we lower the solubility. I called that thermal pollution. Letter B, here we're decreasing temperature, so the solubility of a solid would also decrease. If I drop the temperature, colder substances increases the solubility of gases dissolved in water. Letter C, increasing pressure. For a solid, no effect. If I increase the pressure, I increase the solubility of a gas. Same here. If I drop the pressure of a solid in water, no effect. Pressure affects gases, but if I drop the pressure, the solubility then also drops. This is a very key idea. The next part of our lesson will involve a calculator. So let's pause, find our calculator, and when ready, come back to talk about concentration units. We'll talk about weight by volume, volume by volume percentages, as well as the unit known as molarity. Take a break and come back when ready.